The Smith chart is a very useful tool for doing conjugate impedance matching. So far we have seen the Smith chart to be in the admittance chart, in the impedance chart. But now we are going to look at what is called as an admittance chart. We know that admittance is the reciprocal of impedance. Let's see what the reciprocal of an impedance, that is an admittance, map to in the Smith chart. Let's take a look at it. We know that Smith chart being the representation of reflection coefficient in the complex plane, if for a particular load impedance the reflection coefficient is gamma z, if I were to have 1 over ZL as the load impedance, then turns out that the reflection coefficient that you get for that is exactly the negative of the original impedance. That means that in the Smith chart, the reflection coefficient for the reciprocal of the impedance is going to be diametrically opposite. The -1 in the complex plane means a phase of 180 degree. So it's going to be diametrically opposite in the Smith chart. Let's take a look at it, how it works. So let's identify, first of all, consider a particular load impedance, ZL, identified as this particular point in the Smith chart, having a certain resistance, constant resistance, and a constant reactance. It has a certain reflection coefficient, the magnitude given by this vector, and the phase is given by this angle that it makes with the x-axis. Now, if the diametrically opposite point represented by the minus here means that we are moving by an angle of 180 degrees, in the clockwise direction, diametrically opposite, I end up reading the 1 over ZL, the reciprocal of the load impedance over here. In this particular examples, the resistance and the reactance is of this sort. The corresponding 1 over ZL is of this sort. Both of them are normalized. So we can see that given a load impedance, if you were to have the reciprocal of it, which is the admittance, then you're moving to a point that is diametrically opposite in the Smith chart. And this shouldn't be surprising to us because we have already seen that in a quarter wave transformer, essentially impedance of ZL at the load when you move by a distance of lambda by 4 through the transmission line, the looking in impedance is of the form Z0 square over ZL. So the ZL that you see here has transformed to be 1 over ZL in a quarter wave transformer. And we know that when you travel a distance of lambda by 4 into the transmission line, it is as good as moving a distance of 2 beta L, which is equal to 180 degrees in the Smith chart in the clockwise direction. So we can see that for every impedance point, the diametrically opposite point is the admittance point of that particular impedance point in the Smith chart. Also interesting to note that if we were to go not just by a quarter wavelength, but let's say all the way by a full distance of half wavelength, we end up getting the same impedance as that of the load that is appearing at the input. The same impedance that was at the load appears at the input. So in terms of the Smith chart, we have gone one full circle of 2 pi and heading back to the same point. So the ZL comes back.